The first of our little practice assignments, practice question assignments that we do in preparation for our quizzes last night was practice number 1. And that's on, see, it's concept 12. If you take a look at those booklets that I gave you last week on Friday, lists all these different concepts. C12 is concept 12, momentum. It's what our quiz is on tomorrow. We're going to take a look at all 4 of these practice questions so that we're set up well for tomorrow's quiz. First one says a 47-gram ball is hit with an initial velocity of 70 meters per second at an angle of 30 degrees up from the horizontal. The vertical component of the ball's momentum. What is it? Well, we're going to draw a picture here, okay? It's the first thing we're going to do because it's a little bit easier to visualize, I think, if we can see a picture here. Here's my angle, 30 degrees. Here's my speed, 70.0 meters per second, and I'll just label the mass over here somewhere. By the way, what do we got to pay attention to with this mass? Yep. Yeah, we're in grams here. We got to be in kilograms, right? So let's divide that by 1,000, 0.047 kilograms, or we could just say 47 times 10 to the minus 3. That would work as well. Now, if you were in my class last year, there's a 5-word phrase that is likely going through your mind right now. If you weren't in my class last year, then you know what to do with this. Mr. Coderre taught you just as much as I taught my students last year. You just aren't going to recognize the 5-word phrase, that's all. Rudy Ann, what is that 5-word phrase? I don't like funny angles. A funny angle for us is something other than 0 or 90 or 180 or 270. In other words, 30 degrees is a funny angle. So is 60. So is 45. So is 88. So is 12.7. Anything other than 0, 90, 180, or 270, we don't like them. We don't like funny angles. So what do we do with them? We get rid of them. We have to get rid of it. So let's turn this 30 degrees, 70 meters per second into an X and into a Y every time. And I don't care if this is in the context of momentum, like it is here right now, or whether this is in the context of adding displacement vectors, like it was last year in Physics 20, or adding velocity vectors or force vectors. It doesn't matter. If you have an angle that's not a normal angle, 0, 90, 180, or 270, then this is what you've got to do regardless of the concept. Concept 12, concept 448, doesn't matter. If you've got a funny angle, deal with it. Get rid of it. Now here's how we deal with it. We draw a little triangle around the angle. Make sure the angle is inside the triangle. I don't want to draw my triangle up here because then my angle would be not inside the triangle, it'd be outside of it. It's not what I want. I got to have it inside. So draw my triangle around the angle, and then let's deal with the x and y components. Say cosine 30 degrees is equal to, you guys remember the relationship for cosine? Cosine is equal to, yep. You know, let's go the SOHCAHTOA thing. Yeah. Sorry? Yeah, let's go adjacent over hypotenuse. But yeah, I mean, what you got to be careful with that is, I mean, that's correct. If you're saying R here is 70 meters per second, right? And this is your X component, that's correct. But let's be careful with that because it won't always be X. It's conceivable if you had an angle with the Y component here, with the vertical, then your adjacent side would be your Y component, not your X component. So let's think of it as adjacent over hypotenuse here, okay? Just so we don't make that mistake. Adjacent and hypotenuse. X over 70. Now, I don't know what that works out to be. It doesn't really matter in this case what X is because I'm looking for the vertical component of the ball's momentum, right? I mean, this is how I would do it. Maybe a question on tomorrow's quiz, maybe a question on your unit test. Maybe you have to find the X component as opposed to the Y component. You'd use cos in that case. Here I'm looking for the Y component, so I'm going to focus a little bit more on sine 30 degrees is equal to opposite over hypotenuse. Y is equal to 70 sine 30, which ends up being 35.0 meters per second. There we go. What I've just done is no different than what I would do in any context where I have a funny angle, whether it be a Physics 20 context or a Physics 30 context. Last year, about a month into class, when you were in Physics 20, you could absolutely have gotten as far as you got on this question right now. Absolutely. A month into Physics 20, you could have gotten this far. Now, you wouldn't be able to do the rest, but you could have gotten this far a month into Physics 20, because this is what you always do when you have a funny angle. All right, now we want to find the vertical component of the ball's momentum. Well, momentum is m times v. If I wanted to find the magnitude of the momentum, the overall resultant momentum, then I would say it would be 0.047 times 70. If I wanted to find the x component, I would say it's 0.047 times whatever this is. If I wanted to find the y component, I'm going to say it's 0.047 times the y component of the velocity. So I'm going to say 0.047 times the velocity of 35.0 meters per second. And when I do that, it works out to be 1.65 kilograms meters per second, or A. All right. Now, somebody in period 1 today asked a great question. I hadn't even thought of it, to be honest, but it was a good question. Person said, could we find the momentum saying m times v, 0.047 times 70, and then, what do you think his follow-up question was? Could you multiply 0.047 times 70, and go ahead, and then use SOHCAHTOA, and then say, oh, I don't like my funny angle of the momentum instead of the velocity? Absolutely. Bottom line is, you got to deal with the funny angle. Whether you deal with it like the velocity, like I did here, or whether you deal with it as the momentum, as my student in period 1 wanted to do, it doesn't matter. You're going to get A, 1.65 as your answer. Okay? Is that okay? 2. To be honest, I debated even putting this one on this practice, because really, I should have waited to put this one on until after we did impulse. I mean, we did introduce impulse on Friday, but we didn't get very far with it. But then I thought, you know what? Like, you don't even really need impulse to figure this one out. And lots of you probably remembered that impulse is Newton seconds, which is, of course, going to be valid for momentum, since impulse is change in momentum. But let me justify that for you, okay? Newton seconds. Newton comes from force, right? What's the equation, the most common equation that we would use to describe force? F is equal to? Yeah, F is equal to m times a. So a Newton would therefore be equal to m is kilograms times a is meters per second squared. All right, so let's sub in kilograms times meters per second squared times seconds, right? See what I'm doing here? Replacing newtons with kilograms meters per second squared, and then multiplying it by seconds. That looks like x to the s. Let's do this. Now let's cancel out one of the seconds. One on the top, one on the bottom. What are we left with? Kilograms meters per second. Isn't that the units for momentum? Well, if that's the units for momentum, then Newton seconds has to be units for momentum as well. So you could have remembered that from Friday's lesson, or you could have figured it out. Either way. 3, talk about twists. Man, I like this question. This last semester was on the unit exam. Clearly, it's not this semester. It's a good question. So good and so easy that people overlook the obvious and get it wrong. Lots of people do. Lots of people get this one wrong. Think back to Physics 20 again for a second here. Projectile motion. Remember, for projectile motion, the y component, the up and down component of the ball or the rock or whatever it is, was acceleration. It slowed down vertically and then stopped and then sped up as it came back down. Remember that? What about the horizontal motion? Do you remember how we described that? Yep. It was constant velocity. So if it's constant velocity horizontally, well, then it's constant momentum, right? If v isn't changing, then m isn't changing, then p isn't changing. So if it's 800 here, then it's going to be 800 here, and 800 here, and 800 here. horizontally. Vertically it changes, but horizontally the momentum isn't going to change because there's no change in velocity or no change in mass. So B is our answer. And finally, number 4, you guys actually did a pretty good job on number 4. The most work of any of the questions. It says a 1,200 kilogram car traveling north at 20 collides with a 1,000 kilogram car traveling south at 24. It's the total kinetic energy and the total momentum of this system. Red pen, what am I pulling that out for? What do I want to circle to draw attention to here, Cam? Yep, the north and the south, right? Now, sometimes that's not relevant, right? If I'm dealing with a scalar, then the north and south don't matter. But I'm going to draw attention to it just in case. All right, let's find the total kinetic energy, since that's what we're looking for first. Let's say EK1 is equal to 1/2 of 1,200 times 20 squared. 20 squared is 400 times 600 is 24,000. And the kinetic energy the kinetic energy of object 2, I should say, EK2, is equal to 1/2 of 1,000 times 24 squared. Is that right, 24,000? Or is it 240,000? 240? The zeros just didn't look right there. Thank you. And this one I don't know. 24,000 squared. Can't do this one in my head. 24 squared times 1,000 times 1/2 gives me 288,000. I want to add these up to get the total kinetic energy now. 240,000 plus negative 288,000, right? Because the second one's to the south, right? What does that give me? Negative 48,000? C or D, is that right? Is that right? Ryan, what's wrong with that?
It is negative.
Sorry?
It's not negative.
How come it's not negative?
It is the kinetic energy.
Good. And kinetic energy is a? Good. So we don't pay any attention to direction. We just simply add those up the way they are without regard to north, south, east, west, whatever. We get 5.28 times 10 to the 5 joules. Good. Answer has to be either A or B. Now let's look at the momentum. The momentum of object 1. 1,200 times 20 gives me 24. That's 24,000 kilograms meters per second. This one, P2, is what? 1,000 times 24. Another 24,000. Is that right? Let's add those up. And what do we get? 48,000? What's wrong?
0.
Why is it 0? Yeah, that's going to the south. This is when we have to pay attention to north and south, right? Because momentum is a vector. Add these up, gives me 0. So our answer would be B. Good. Okay. Friday, we introduced the concept of impulse. We said impulse was the change, or is the change in momentum experienced by an object. And now we differentiate that with straight momentum, which is the product of an object's mass and velocity at a specific moment in time. So momentum talks about a specific and instantaneous time, whereas impulse talks about a time interval, a change in momentum over a certain amount of time. Impulse, just like momentum, is a vector quantity, but the direction of it's a little bit harder to deal with than momentum is. You remember that momentum is to the north if the velocity is to the north, or momentum is to the west if the velocity is to the west. But impulse is trickier. If we have an impulse Sorry, if we have a momentum that's to the north, let's say this object is moving at 10 meters per second to the north, its momentum will clearly be to the north. 5 seconds later, we have a momentum that is, sorry, a velocity that's 15 meters per second to the north. That means we've gained velocity. If we've gained velocity, then we've gained momentum, and that will be a positive impulse. The impulse will be positive because it's a gain in momentum in the positive direction, in the north direction. Now, we could look at this another way. Say, instead of speeding up from 10 to 15 meters per second, let's say now it's going from 10 meters per second to 5 meters per second, still north. In this case, we would say we have a negative impulse. This is a positive momentum and a positive momentum, but the impulse is negative. And we would say that, we could think of it actually in terms of two different ways. A, we could say that we've lost momentum, right? We have a loss of momentum in the positive direction. We went from 10 meters per second to 5 meters per second. We slowed down. We lost momentum in the positive direction. But we could also think of it as being an impulse to the south, right? The impulse is something here. It's something less here. It's a negative impulse. That means the impulse is to the south. How can we have an impulse to the south when the momentum initial and the momentum final are both to the north? Because the change in momentum is to the south. Right? What direction does the force need to act in order to cause this thing to slow down? Well, the force needs to act downwards to the south. Therefore, if the force acts downwards, the impulse is downwards as well, or to the south. Does that make sense? So momentum is easy for direction. It's always the same as velocity. But impulse, a bit confusing, right? Because we can have a momentum to the north, another one to the north, but yet my change is to the south, or a negative value. We talked finally about Newton's second law on Friday, and we remember that for physics 20 is F is equal to m times a, and then we replaced a with delta v over delta t, and we end up getting F is equal to m times delta v over delta t, which we turn around and rearrange. We get this, F times t is equal to m times delta v. There are the two parts of the equation that appear on my data sheet for impulse. Remember I said on Friday that we want to write in delta p for that? Write that in on your data sheet. Remind yourself that m delta v is impulse. So is F times delta p impulse. Don't forget that it's delta p. Finally, the units, m times delta v, kilograms meters per second, or F times t is Newton seconds. Now, we did a problem on Friday. We're not going to do this again. But I want to just point out a couple of little things before I let you actually work on some questions yourself at your desk. Okay. A couple of things. Number one, we got a north-south here. No matter what the context, we always have to remember that. Even if it's kinetic energy, we want to be conscious of that. And then we realize later on, oh, wait, well, we don't have to worry about positive and negative north and south. But we always want to immediately notice that. Okay, when we see north, we see south, notice it, because usually that means positive and negative. Secondly, we're going to solve this whole thing using impulse. We're going to solve for the first part of it using impulse because it asks for impulse. Right? That's not rocket science, right? I got a son in grade 8. I got another son in kindergarten. I don't know if the kindergartner would say this, but I can tell you the grade 8 would say this. He doesn't know anything about impulse or momentum. Nothing. But if I said to him, here's the problem. Determine the impulse experienced by the car over 35 seconds. What are you going to do? He'd say, use impulse. He doesn't have to know what that is to know that that's what he's going to do, right? Use impulse to solve that question. Okay, that's an obvious one. Sometimes you're asked for the change in momentum, the momentum gained or momentum lost. Use impulse for that as well, because it's what momentum gained or lost means, impulse. But this is the one that people overlook. And this is the one that's a little bit more subtle. If we see a force and a time in the same question, then that leads us to use impulse as well. even if the word impulse isn't mentioned, even if the word momentum isn't even mentioned. Use impulse if you see a force and a time in the same question. You're going to encounter that in the worksheet that you're going to do in a couple minutes. A couple situations where maybe it doesn't look like an impulse question, but you see a force and a time in the same question. You're going to know to use impulse to solve that question. All right? The worksheet is worksheet number 2. There are 9 questions on this worksheet. I want you right now to do questions number 1 to 8. And we'll give you some time to work on it at your desks and to ask questions from me as I walk around, taking a look at what you're doing. All right, have a look up here, everyone. We're going to do number 1. It says a force of 20 newtons is applied to a 3 kilogram object for 4 seconds. What's the impulse experienced by the object? This could be done by using F is equal to m times a, and then multiplying the force by the time and so on. But that's not the way we want to do this today. Okay, I'm not even saying that that's necessarily a bad way to do it. It's just today we want to get used to using impulse to solve questions. So that's what we want to do for all of these questions today, including number 1. We know this is impulse because we're asked for impulse. Remember, if we're asked for a gain of momentum or we've got a force and a time in the same question, we're also going to use impulse. I think that rears its head in question number 4, actually. Let's write down some givens and then see exactly what we're going to do here. We've got a force of 20 newtons, a mass of 3 kilograms, in a time interval of 4 seconds. We're looking for delta P. We know from our data sheet that F times T is equal to M times delta V. And we know because we wrote down right beside that on our data sheet that delta P is equal to that. We're looking for this. We've got force and time. We don't even need M and delta V here, do we? If we multiply F times T, then we've got impulse. That's exactly what we're looking for. So let's say F is 20 newtons. Delta T is 4.00 seconds. That gives me 80 kilograms meters per second, or what could we have done besides kilograms meters per second? Newton seconds. Good. Is that okay? Okay, keep working. A few minutes, we'll go over another one. All right, I want to extend this just a little bit. Let's say that Dylan and I are running down the hallway in opposite directions. Dylan, what's your weight? What do you weigh? 110? Really?
I lost 40 pounds when I got my wisdom teeth.
Holy cow. All right. Okay, I picked the right guy to collide with in the hallway then, I guess. So Dylan's running down the hallway, 110 pounds. Boy, I thought I was late. I'm about 150. I thought I was late. And we smash into each other. Now, when we smash into each other, we're both going to change velocity, right? Like one guy maybe speeds up, one guy slows. Maybe we both slow down. Whatever. We're both going to change velocity. We have different masses, but we collide. We both change velocity. What if Dylan is running one way and I'm running up behind him and I tackle him from behind? Well, we both change velocity again, right? If we both change velocity, we both experience an impulse. Impulse is a change in momentum. We both change velocity. We both experience an impulse. Now, listen carefully to what I'm about to say. Regardless of whether Dylan and I both have the same mass, regardless of whether Dylan and I are both going in the same direction or opposite directions when we collide, regardless of whether it's a head-on collision or a rear-end collision, two cars colliding with each other, regardless of any of that, if Dylan gains momentum, then he must have got it from me. So if he gains 10 units of momentum, then I must have lost 10 units of momentum. If Dylan loses momentum, then I must have gained momentum. In other words, the big takeaway from this is this. If Dylan's impulse is 10 during that collision, then my impulse will automatically, we know 100% for sure, will be negative 10. Got it? If one guy gains, the other guy loses the exact same amount. That's the case with force as well. That's physics 20 concept. Remember back in physics 20, you learned Newton's third law? For every action, there's an equal and opposite reaction. Or if object A applies a force on B, object B applies an equal and opposite force on object A. The forces are equal, but opposite. So is the impulse. If one of them gains, the other one's got to lose. If the impulse on one is plus 16, the impulse on the other one has to be negative 16. Always, regardless of whether our masses are the same or not, regardless of whether our original directions were the same or not, regardless of whether we stick together as we go off, right? Because we're wearing Velcro jackets or some, I don't know, or whether we bounce off of each other, doesn't matter. Regardless of whether we're both going in the same direction or opposite, right? It doesn't matter, right? One's plus 10, the other's got to be minus 10 every single time. If there are two objects colliding, the momentum gained by one object will always be equal in magnitude, but opposite in direction, to the momentum lost by the other object. This is regardless of the masses or the velocities of the object. All right, one more little thing before I give you an example, and then we'll wrap it up for the day. We talked about that collision between Dylan and I. If Dylan gains a certain amount of momentum, then I must have lost. If I've gained, then Dylan's lost the same amount of momentum. If you want to analyze that collision mathematically, like take some equations, analyze it mathematically, using impulse. Okay, there's another concept that in a few days we'll actually learn you could solve a problem like that with. But right now, using impulse, you got to make sure of one thing. I mean, there's a few things, right? Direction and all that stuff, right? But one new thing, and that is this. Pick one object, not both. So if you're analyzing that using impulse, don't use Dylan's mass and my mass. Don't use Dylan's velocity and my velocity. Either use data for Dylan or use data for me. Now, listen carefully. If the question says, what is Dylan's impulse, but you know nothing about Dylan, it's okay to find my impulse because we know Dylan's impulse is the same value, right? So what's Dylan's impulse? How do we solve that? We don't know anything about Dylan. What's his mass? What's his change in velocity? Well, as long as you know my mass and my change in velocity, and you can get my impulse, then you know Dylan's impulse will be the same, but opposite. So don't worry about which one you're asked to solve for. Solve for either one of them, because the other one is just going to be the same value. You're always going to get the right value, the right magnitude, if you pick one object or the other, but not both. All right, we're going to take a look at one example that unfortunately is not on that page that I handed out to you the other day. Don't worry, there won't be very many of these where you have to copy out the example. Lots where you have to copy out the solution, not very many where you have to copy out the question itself. This one says a 1,200 kilogram car traveling north at 10 collides with a 1,000 kilogram car traveling south at 10. Look at this already. I noticed this, north and south, circle it in red. The two cars entangle and head off as one. That means that they stick together for whatever reason. Maybe their bumpers interlock or some fenders dent and interlock somehow or whatever. They head off as one object immediately after the collision at 0.901 meters per second to the north. The collision itself lasts for 0.08 seconds. So it's over before you know it almost. And they're just heading off as one object after that. We want to find the force of impact on the lighter car and the force of impact on the heavier car, both. What do you know about this force versus this force? What do you know about those forces? So what? They're equal in magnitude and opposite in direction. Good. So if one's plus 10, the other's minus 10. The forces are equal. Now, you're not asked to solve for the impulse, but we know that the impulses would be equal and opposite as well. Now, remember what I said earlier on today? If you see force and time in the same question, use impulse. Even if the question doesn't mention the word impulse or doesn't even mention the word momentum, use impulse. Remember what else I said? If you want to use impulse to solve this question, Dylan, what do I got to make sure I do? pick one object. Pick either the light car or the heavy car. Diamond, which one do you want to do? The 1200 or the 1000? Sure, okay, the 1000. That's the lighter car. Doesn't really matter, right? Let's say F times delta T is equal to M times delta V. It's all equal to delta P as well, but we're not going to use that part of it. F is equal to M times delta V over delta T. We get 1000. Oh, careful here. Delta V, VF minus VI. VF is 0.901. VI is negative 10. So we're going to subtract negative 10. Divide that by the time of impact, 0.08. We're going to solve that. So 1,000 times bracket 0.901 minus negative 10. Whoops, that's not what I wanted to do. 1,000, again, try it again, times bracket 0.901 minus negative 10, end the bracket, divide by 0.08. You get a force of 1.36 times 10 to the 5. Megan, what do you think it would have gotten if Diamond had said, pick the heavier car, the 1,200 kilogram car? What do you think my answer would have been? Same one? Yeah. Same number, opposite direction. Negative 1.36 times 10 to the 5. Good.